All right, so we are told that we have, in number 2, a piece of metal, and it's under the stress state below between two rigid plates. So, metal, what do I know about a metal? Young's modulus, 100 gigapascal, nu is equal to 0.3, and I'm going to pull out Mathematica at this point and start to basically fill out this problem. So Mathematica is a fantastic tool to solve these systems of equations simultaneously. Highly recommend you to utilize it in your exam if you've been utilizing it in your problem set, and hopefully you've been doing that as well. So y equals 100 times 10 to the 9, nu equals 0.3, excuse me. So got some of those values down in R. So I have my coordinate system, that's step 1. 2, I've kind of written out all the properties that I know, and now I need to basically, I have the rigid plates are rigid. Nice problem, Josh. But they're well lubricated. So we see this kind of stress state given here. So my stress state in step 3, I need to find out my stress state and my stress tensor and my strain tensor. So I know that in the 2-2 direction, there is 10, and then all this is in kPa. So my sigma 2,2, I know that value. I also know, so when I pull out sigma 2,2, in the 1,1, there's minus 85 as well. So when I basically pull the material here, so this is stretching it, so this will cause the 3,3 direction to decrease, but I'm pushing basically more in that other direction, a larger value, so I know that the material is going to basically pop out in the 3 direction, but it's constrained by those basically walls. So I know that my strain in the 3,3 will be 0. I'm going to have a strain in the 1,1 or the 2,2, excuse me. I'm going to have a strain in the 1,1 as well. And because it's popping out, because those walls are going to prevent the expansion, then I'm going to have basically a stress in the 3,3. So my unknowns are 1, 2, 3. Luckily, I have 3 equations. The rest of those values are 0 because we know that we are well lubricated. So I'm going to go ahead and say sigma 1 equals minus 85 times 10 to the 3 because it's kilopascals. My sig 2,2 is equal to 10 times 10 to the 3. And then my E33 is equal to 0. And there we go. Now I'm going to solve E11, set it equal to 1 divided by y times sig 11 minus nu times sig 22 plus sig 33. And you can now copy this. If I'm going to solve multiple equations simultaneously, I need my squiggly brackets, comma, comma. Here we go. And then I need to solve for sig 33, E11, E22. Solve for those all. I need to change these equations. So E22, this is going to be sig 22, this is going to be sig 11, this is E33, this needs to be sig. Again, I love working with linear isotropic elastic materials. And now we can go ahead. Numerically solve, doesn't like that. Just go ahead and do that. So I have my values. So you see here that I'm going to have some strain in the 1,1, which is going to be, even the strain in the 1,1 was going to be negative, fantastic. E22, positive, makes sense. And then sig 33 is negative compressive because the material wants to bounce out. Looks reasonable to me. So I'm going to give these values right now. Sig 33 equals this. My E11 is equal to this. And my E22 is equal to this. Fantastic. So write out the values of the principal stress state, all 3 normal values, as well as the value of maximum shear and the rotation to get to each of these states. So if I look at my stress tensor, actually up here, so I see that I have sigma 1,1, sigma 2,2, sigma 3,3. So I am already in my principal stress state. So my sig 1 is equal to sig 2,2. My sig 2, because again, I'm looking at the actual, like, real numerical value. So if it's positive, it's greater than the negative. Let's see, let me sig 1,1, I want to look at it. Yeah, so sig 2 is equal to sig 3,3, and sig 3 is equal to sig 1,1. So those are those values. I know that if I draw my 3D Moore circle, if we're in, because we are in our principal stress state here, so tau stress. So if I'm in my 3D principal stress state, I'm going to have basically looking at my sigma 1, my sigma 2, and then my sigma 3. So I'm going to draw a circle like this, draw a circle like this, and I'm going to draw full the 3D Moore circle like this. So my maximum principal stress rate will be sigma 1 minus sigma 3 over 2. And there we go. So do that. So that'll be my maximum value of shear, sigma 1 minus sigma 3, the whole thing divided by 2. And there's my value. So the rotation, 45 degrees, again, because we're already in that state. So fantastic. If the rigid plates were not well lubricated, write out the full stress and strain tensors, write out the equations because you do not solve because you can't. So what would change here? So I could have some shear basically like this. So what would the shear there be? So the normal would be in this direction. This would be basically like I'd have a sigma 3-1, and thus I'd have a sigma 1-3 component. When I'm pulling here, I could also have a shear in this direction, so that would be again a sigma 2-3, a sigma 3-2, and then can I ever have a sigma 1-3? Probably not really. Sigma 3 in the actually no, I definitely do have sigma 3. I was actually thinking of a 1-2. So in the one direction, pointing in the one, pointing in the two, so coming out. Not really. So I think those are the only other components there. So you just have those additional shear components, and thus I'd also have an epsilon 2-3, epsilon 3-2, and an epsilon 3-1 equals an epsilon 1-3. Excellent, excellent. Turns out this material we're working with is one of the 4 mystery alloys illustrated in the stress strain curves below. These metal alloys tend to yield when the maximum shear stress exceeds the yield stress. Which material, if any, will yield? So all of these materials tend to yield at these are values of like hundreds of megapascals. My maximum shear stress here is 47, it's basically like 48 kilopascals. So none of these materials are going to yield at all. So they're well beyond those values. Excellent. So now let's get on to question number 3, and I'll see you in the next video. Thanks. Bye.